R square 0.94, adjusted R square 0.93. So it's giving at least more than 90%, accuracy. This is more than 90% of the variance in the sale prices explained by this model, the overall model. There are a bunch of NAs sitting here, which is just to indicate that these columns are also redundant. It so happens some of these columns are identical to some other columns. This can happen, in a huge data set where some of the columns are, it so happens, this particular column is identical to some other column, or it's exactly a linear combination of some other columns. So it throws NA there. And those are the redundant columns. Now, you can't have a model with redundant columns. It is not going to work in prediction. You need to drop them off. So I'm going to create a formula which pulls out where the coefficients are NA and pull out the names related to that and then drop them out in the next model. So the formula that I have, I just created this formula, which is log sale price tilde dot minus all those columns which have which are redundant, basically. Actually, so some of these things you can understand. Actually, total basement SF, that is, let's say the total basement area in square feet. That's what it means, and that is actually nothing but the sum of two variables here. So some of these ways, some things like this are there. See, basement type 1, basement type 1, basement type 2, and so this is. And these two are the area in square feet. Now, if you just add these three up, it should give you the total basement area. So that's why it was throwing up those NAs. So I just dropped them off and then build the model, which can then be used to predict the output for the test data. Notice that I'm taking now this data with 1:n row of train. That is, say the first half. I just pulled out. Remember, this was a combination of train and test, put one next to the other, one below the other. The test were put below the train, and then converted to dummies. Now I'm just taking the training part alone, building the model. Okay, then use the predict function. Now apply it on the testing part, that is data of the other part. 1:n row of train is the first half. Now you take the second half of the data, n row of train plus 1:n row of data. That is the second half of data. That is the test data. Then you use the model, make a prediction, write it in submission. I just wanted to check the advantage or disadvantage of using PCA. So this is without using PCA or any dimensionality reduction at all. Right? You have just 269 predictors. Okay, less than that because some of the predictors are redundant. But after you have a bunch of redundant predictors, then you're removing the redundant predictors, you build the model. You don't do any dimensionality reduction. All we have done is to simply normalize. By the way, in scaling the variables to 0 to 1, so that the minimum goes to 0 and maximum goes to 1, am I going to be affecting the outcome of the regression, linear regression? Is it going to have some? No? Why not?
The output will also be scaled accordingly.
Yeah, so in a linear regression, all you are doing is when you scale the variables, you will just be the model will simply give you, it will simply adjust the slope accordingly, so that it predicts the output. But the accuracy of the model is not going to change. It's irrelevant. It doesn't matter whether you have scaled the variables or not. Now it will matter when you are going to do linear combinations of the variables. When you are going to do PCA, it will matter that you have scaled them. If you don't scale them, then the variables which are having huge numeric values will dominate, right? The sale price is huge, so it will dominate automatically. That is why I'm scaling them. But for the linear model itself, its scaling is not an issue. It doesn't matter whether you scale it or not.
The slope on the y-intercept remains the same, right?
Yeah, the slope will just be adjusted accordingly. That's all. so that but the accuracy doesn't change. When you scale the predictors, the slope will just be adjusted. It will be absorbed into the slope. That's all. So it doesn't matter. But I'm scaling them in order to give equal weight to our PCA, which we'll do next.
Oh, you mean to say the slope will change and it will get adjusted. It's not like the slope is going to be constant.
Here's the thing. See, if I just take one of these columns and multiply it by 10, then what will happen if I build if I build the linear model, the slope will just be adjusted accordingly, so that finally you get the same output, right? You will get the same predicted output. It will just be the slope will then be adjusted by 1 by 10, divided by 10, so that finally. So it doesn't matter, but the accuracy is irrelevant. Accuracy is not going to change. It doesn't matter. The accuracy is because when basically the accuracy is measured by this R square. And remember, R square is a normalized result. It is normalized by variance and so on. So it doesn't matter. It will always be between -1 to 1. R will be -1 to 1. R square is 0 to 1. So yeah, the reason I scaled it is because it is useful for PCA. That's all. Now you write it in, and the score I calculated was 0.146. I'm submitting it to Kaggle. Did we do this in linear regression? We submitted to Kaggle, right?
Yes, sir.
So yeah, you remember getting something like this, 0.14 something. I think we dropped off a few variables and then used a smaller data set. But yeah, you will get something like this. But we are using here all the predictors, getting a score of 0.146. Okay, so now we'll do PCA. Now there are a lot of functions and packages for doing PCA. This is called PR comp.
What does the score indicate? What is the score? That
the score, if you remember, yeah, the score in Kaggle is how do you measure the accuracy? In Kaggle for this linear regression, they are using root mean square error, right? That is the score they are using. So this is it's not just root mean square error, but root mean square of the log of the error, which means to say that basically it's that on average the predicted value is about 14% higher or lower than the actual value. That's what it is. And of course, the smaller the score, yeah, the smaller the score, the better your model.
Okay.
But on average, it's 14% higher or lower. That is the interpretation of the score. So PR comp. Now PR comp does principal component analysis. So you just put the X directly. The X is all the entire data set. So you just want to drop out only the outcome. That is only the sale price we will drop out, and all the rest will be sent to this PR comp. It itself can do its own centering. Remember that we had to center it. Centering is good. It allows you to kind of it brings the variables more closer to each other. Make sure that they are more uniform. So centering means you subtract the mean of each variable, so that now the changed variables have mean 0. So that's what is centering. Scaling is you divide by the standard deviation. So all the standard deviations are now 1. You can do that because that is one way to make sure that before you do principal component analysis, you make sure that all the columns have 0 mean and standard deviation of 1, so that they are now all on the same footing. Now I haven't done that for standard deviation. I have allowed center equal to true, but I have not put scale equal to true. Anyway, we have already scaled them between 0 to 1. So all the standard deviations are going to be anyway more or less on the same scale, more or less. I mean, this is, of course, here the range has been set to between 0 to 1. If you want to put the standard deviation to 0 to 1, you have to divide by standard deviation. So what this does is actually, it just calculates the variance covariance matrix of the entire data set that you have provided. So data of minus 37 means it will just drop off that column, the sale price column, take all the other columns, which is the remaining 268, and then calculate the variance covariance matrix. So that will be 268 by 268, and then diagonalize it. Diagonalize it, get out the eigenvalues and eigenvectors. That's what PCA does. So now you'll get out. What will you get from that? So that returns an object of type principal component, and that contains it contains the standard deviation of the principal components. Now this will be arranged in descending order for PC1 down to PC268. Obviously, there will be equal number of as many predictors as there are, that many standard, that many number of PC principal components will be there. So the highest one has what, 1.1, and then it keeps going down. The standard deviations of the principal component. So PC1 will be the highest, and then this is the standard deviation of PC2 and standard deviation of PC3 and so on. There are a bunch of results here which you see. Notice that these are essentially 0. That is to say that there are a bunch of variables which are totally redundant. They are absolutely useless. So the standard deviation of those principal components are down to 0. They are exactly 0. You see 10 to the minus 16 and all is just round off errors, result of rounds. These are identically 0. But it goes down to 0.002, and then you have
Your voice is lost. Hello? Hello? Your voice is lost.
Saturday class.
Hello?
Yes, sir.
Hello? Yeah,
Yes,
you can
hello.
hear me? Yeah, I think the problem is this, the hotel, the Wi-Fi just keeps going off and on. So sometimes it just takes me off. Okay, so the principal component 1 and the way in which you can calculate that from the original data. So PC1 is nothing. These are the A1, A2. Basically, these are the coefficients with which you multiply the original data to get PC1. And you can get back the original data themselves by simply taking the transpose of that. So you can just say MS subclass equal to 6.6 into 10 to the power of minus 3 times PC1 minus 7.23 into 10 to the power of minus 2 times PC2 and so on. If you want to get back the original from the principal components. So These are
right now,
these.
yeah, for example, can you just go, for example, the PC1. Can you just show me the?
Yeah, we want to see PC1. Okay, so
Yeah.
PCA dollar rotation of comma 1. So yeah. Now you want to see, okay, PC1. Let's look at which are the variables which are actually contributing most to PC. This is PC1.
Yes.
It's the first column. The first
That is
column of the rotation matrix. Okay.
Yeah, so M subclass, that is 6.616 into 10 power minus 3 into subclass plus 1.34 into lot frontage plus 3.22 times lot area. Something like that will give my PC1, is it?
That's right. Yeah.
Okay.
So this is the rotation matrix. It just rotates, taking linear combinations of the original variables to generate the principal components. We can actually find out which are the variables that are contributing most to PC1, and they are most likely going to be the variables which convey most information about the outcome also, because they are the variables.
Correct. Agreed. Yeah.
Because they are the variables that are actually having most variance. They change a lot from one instance to the other, from one record to the other. Whereas those variables which are like a constant throughout, they are not going to convey much information. So if you want to, you can look at which of these have them. Yeah.
Sorry for the interruption. So for PC2, will the same variable be part of PC2, or is it like the variable which is defining PC1 the most should not be there in PC2 because they should be independent?
Well, yeah. See, the thing is that the contribution of, say, suppose let's look at the contribution of variable 1 to PC1 will be inversely proportional to its contribution to PC2. There will be a relationship. You'll notice that. Let's go back to this image. See, okay, so this is PC1, right? The contribution of X1 to PC1 is more than the contribution of X2, right? Right. So, and okay, let's look at it the other way. That is to say, you're saying, okay, in PC1 there is a lot of X1, right? Because it is more or less parallel to X1. That is closer to being X1. So in PC1 there is a lot of X1. Does that mean that in PC2 there is less of X1? That is the question. Does that imply? Yes, it implies. Yes, it implies that. It has to be, because the total contribution has to, it has to sum out to be equal to 1. Essentially, take the rotation matrix. Where is it? PCA dollar rotation matrix. Let's view that. This is going. What will be the dimensionality of the rotation matrix? It will be 268 by 268, right? 268 predictors, 268 outcomes. So you're seeing only the first 100. So MS subclass contributes this much to PC1, but if it contributes that much to PC1, then there is less of it to contribute to PC2, and so on. It has to be like that, right?
Okay.
So there is a relationship. Same thing with the other way also. So PC1 has more of one, means it has to have less of the others, because they all have to be there. There is a normalization. MS subclass contributes a certain amount to PC1. That means it contributes less to the others, and so on. Oh well, it contributes a lot to PC3. It contributes like 0.14 and so on. Suppose you take all sums of PCA dollar rotation to the power of 2. See, they are all normalized. That is, say, PC1 is going to have the contribution of MS subclass and lot frontage, etc. You just take the sum of the squares; they have to be 1. So I mean, the total weight has to be, there is a certain breakup. PC1 is broken up by this kind of breakup. So similarly, MS subclass is broken up like that.
Okay.
See, row sums also is 1. They're all one. It has to be. So what is this? I mean, I don't remember what is the. There has to be some mathematical term for this, right? They are okay. So if and also of course PC1 will be perpendicular to PC2 and so on. That you will see. This comes from the fact that the eigenvectors are not only orthogonal but they are also normal, orthonormal.
So the row sum and column sum for each of them are summing to 1.
Yeah. So
the sum of the squares are 1, right? Okay.
Yeah, sum of the squares are 1. The squares. What matters is the squares.
Right.
So basically, PC1, if you think about this, what is the sum of the squares? It is nothing but the square of the Euclidean distance, right? So the length of PC1 is normalized in when you're calculating the length of PC1 as a vector in this space, in the space of the original. PC1 is a rotation, but it is not it doesn't increase. It's a search for a particular rotation within this space, but it is not a scaling. It's only a rotation. So the length of PC1 is fixed, but it's just a matter of searching through. So if it is fixed, that means certain whatever MS subclass is contributing, if it is contributing more, that means the others will be contributing less, and so on. And the same thing is the other way around also. MS subclass is a rotation of PC1 to PC268. So you rotate back essentially. This is a way of rotating it back. So the same thing.
Voice got broken the second part.
Yeah.
Your voice got broken for the second sentence. Sorry about it.
Yeah. So it's a rotation back. So both of these are rotations of each other. So you rotate along the original and you get PC1, PC2. Then you rotate back from PC1 to PC2 and get back, you get back the original. Yeah.
Okay.
So that's why the row sums and col sums of the squares
comes
out to be 1, right? So I'm just plotting the cumulative graph of the variances so that you get an idea of how many principal components to keep, because the whole point is to keep a fewer number of principal components and still retain the as much of variance as you want. The total variance of the data, we want to retain as much of it as possible. So I take the standard deviations, take the square. So that is the square of the standard deviations is the variances. Take the cumulative sum. You know what is a cumulative sum? That is, you just take, PC1's variance, and then you take the next will be PC1 plus PC2, the next will be PC1 plus PC2 plus PC3, and so on. Take the cumulative sum and divide it by the total variance of the entire thing. That is the sum of the all the variances. And plot them. What you get is, along the x-axis you have, say, PC1, PC2, PC50, PC100, and all the way down. And if you take the first 50 principal components, what is the percentage of the total variance retained? Nearly around 80%. If you take the first 100, nearly around 95%, right? 92, 95%, something like that. So if you keep only the first 100 principal components, and the original data has these 268 variables, you can bring it down from 268 to 100 while retaining, keeping only those 100 variables. We can still keep about 95% of the variance in the original data. And because the principal components are arranged in descending order of variance or descending order of standard deviation, you just take PC1 to PC100. Those will be our principal components of interest. So you bring down the number of variables from 268 down to 100 and keep only those and use them as the predictors in the whatever model you want to build. So this is a preliminary step. So using dimensionality reduction, bring down the number of predictors and then use them. So first of all, you use the predict function on the principal component object and then use the new data equal to. You can either do that or you just do matrix multiplication. You do the proper matrix multiplication on the rotation matrix, and you will be able to get the principal components. You don't need to use the predict function. Predict function does exactly that. It just takes the basically it takes the original data and multiplies it with the rotation matrix. So think about this. The original data is MS subclass, lot frontage. Each of these are the columns, right? So the way in which you do, so take this data. So data multiplied by PCA dollar rotation in the matrix multiplication sense will be able to give you the PC1, PC2 and all. You see that, right? You take this row and multiply it with this column, because this row will be, well, for one house, this is MS subclass multiplied by the contribution of that into PC1 plus lot frontage multiplied by the contribution of that into PC1 and so on. So you want to get PC1, you just take the original data and do a matrix multiplication with the rotation matrix. So what is the shape? DIM of data. This is obviously 2919 is the number of rows. 269. Oh, we need to drop off the sale price. Right. So 2919 by 268. These are the 268 original variables, and then you have the rotation matrix, dimension of ECA dollar rotation. What will be the dimensionality of this? 268 by 268. You will take the 268 original variables, convert them to 268 principal components. Now you can do matrix multiplication of these, and you will get your PC1 and PC2 and so on for all of them. So you do matrix multiplication of this, you will get for all the records for train and test data, get the 268 principal components, out of which we can retain the first few because it has been arranged in descending order of variance. So you just take the first 100 and they will contain the most variance. That's what they are doing here. Is they're just doing using it using the predict function. Using the predict function, PCA and new data. Now, of course, you can the advantage with the predict function is that you can apply it to some new data as well. That is, you have some more records. Then use the same predict function to get out the principal components for the new record as well. And you take the first 100 columns. That is the PCA data. It keeps about 90% of the variation. If you want to see, okay, how much of the variation is kept, I think you can see it there. It's a PCA dollar. You will be able to see it in summary of PCA. That will tell you essentially the cumulative sum of the cumulative proportion of the variance. Okay, so it is not just it tells you the standard deviation of each one of the columns, but it also tells you the cumulative proportion of the variance. That is, how much of the variance you are keeping. The first principal component itself contains 12% of the variance. PC1 plus PC2 has 18%. PC1 plus PC2 plus PC3 has 22% of the variance, and so on. You go down to PC100 and you would have probably gotten at least 90%. Right? So PC90, contains 90% of the variance of the total data. So keep 90% of the variance and build the model. So now you get the transformed data.pca from the PC. Now this consists of linear combinations of the original data, PC1 to PC100. And now we can use these in whatever model you are building now, whether it's linear regression or whatever. Now we are going to use linear regression because we want to compare and see what PCA is doing for us. But whatever be the model you are using, you can use these now. Drop off the original variables, use these to make a prediction on sale. So, okay, I'm just now adding sale price now to new data frame. Now build the model.pca similar model to what we had, the same linear regression, same trick of using log of sale price. Now, of course, it will, the multiple R square will be less. Naturally, it will be less because we're using number of variables. The question is whether you are avoiding some overfitting. Say, when you are applying it on the test, is it going to help you avoid overfitting or not? So now the same story is done. Use this model, apply it on the test data. Notice the test data also has to be transformed. The test, whatever transformation you do on the training data, the test data. So that's why I'm doing it in one shot, and then just pulling out the test part of it after that. And the score I got was 0.15, which is actually slightly more. It is the so okay. So what we got there was 0.146, right? And we get 0.15, which is more or less the same, slightly more. So it is slightly worse than the original data, but still you would actually prefer a model which is having fewer number of parameters and still getting almost as much accuracy rather than that unwieldy model that you had at first. So that is what PCA is doing for you.
But here, once when we hit the 100 variables, the first 100 variables, we were expecting about 90% accuracy, right? But here, the adjusted is only. Are you able to hear me? Sorry.
It's kind of getting cut.
Now, first 100 variables, if we are taking it, our aim was to hit 90% variance, whereas the adjusted R square here with 100 is showing only 87%. So
that's right. See, there will always see the thing is the adjusted R square and multiple R square. These are all measures on the model itself. The model is built on the training data. Of course, if you keep on adding more and more columns, that will definitely be better and better. In the sense that for the training data, the accuracy will keep on increasing.
If
you let us take it to the logical extreme. Now, suppose you had 2919 columns as well as 2919 rows, then you will get 100% fit, right? Because you will be able to fit everything. You'll have a model that is complex enough to fit it all beautifully, but that is obviously useless because it's not going to fit that well with the test data. So the multiple R square is just a measure of how good it's fitting on the training data, but that doesn't tell us how bad the overfitting is until we check it out on the test data. And here it turns out that if you keep 100, you're still getting slightly worse, but taking into account the fact that this has just 1/3 of the number of predictors, it is still amazing that you are able to get a score which is really the same as that. And of course, if you try SVD and if you look at SVD and factor analysis, which we'll do later, you will see that it will actually improve the score. It will improve it on top of the original model. Here, if you can try out with 150 and see whether it improves. There may be a case where it improves. If you just drop off the last 100, the last 100 are most likely not going to be useful. Just keep 150 and see what the score is. It might actually slightly improve over the original model, because the reason is because the last few predictors are really useless. They are just adding error. They are not helping you in actually building a good model. They are just adding errors. So so it turns out that here PCA with the first 100 principal components is not really improving it, but still it's an improvement in terms of the simplicity of the model. You are having fewer number of parameters, fewer number of columns, and you're still getting nearly the same score. But SVD and all, it does a better job in this case. SVD and factor analysis actually does a better job. It actually improves your accuracy, as we'll see next. So this is PCA. You can look at it on, say, let's look at PCA on some more simpler data set, just to, it may be easier to see it there. So I think we have worked on the iris data. Remember the iris data? So what it has, what? It has 4 numeric columns and 1 categorical column. We will drop off the categorical column and just analyze the numeric data themselves. So this is 4 columns. So each one of these points can be thought of as a point in 4-dimensional space. And then we rotate. You will get 4 principal components out of them, and see whether, okay, whether you can get most of the information about the data directly from the first few. Obviously, because there are only 4, you can't really do much of a dimensionality reduction, because you have anyway a fewer number of dimensions. But still, you can keep, say, the first 2 principal components and see how much information they contain. So, okay, for some reason they have taken a log of this. This is probably, it brings down some variance and all that. Now they are doing centering and scaling here. Center equal to true and scale equal to true. So it before you do the principal component analysis, you subtract out the mean of each column and divide by the variance on each column. So bring the mean to 0 and the variance to 1. This is the summary of the PCA methods. These are the standard deviations. There are 4 principal components. This is the standard deviation of the first one, standard deviation of the second one, standard deviation of the third one, standard deviation of the fourth one. And this is the rotation matrix, 4 by 4. So there is, so think about this, which of the original variables is contributing most to PC1? Can you tell me? Yeah. Hello.
Step on length.
Yeah, the one which has basically the maximum absolute value. Remember, the negative values doesn't matter. Okay, the negative values doesn't matter at all. It does. It really we are interested in the absolute value. So petal length is what matters in PC1. Or petal length has the most impact, and petal width has the next most. Then sepal length and then sepal width. And what matters is the absolute value. So in PC2, what is contributing most?
Sepal width.
Yeah, sepal width is contributing most. The negative values doesn't matter at all, because if you just think about it, it's just the x-axis can be converted to -x. It doesn't matter at all. This suppose this arrow is here, then of course that will be gotten from -a1x1 -a2x2, but it's still the same component. So the negative values doesn't matter. What matters is the absolute value. So PC1 seems to have kind of more or less equal weight between these 3. Notice PC1 has more or less weight between, say, sepal length, petal length, and petal width, but not that much of sepal width. So that goes into PC2. Okay. So see, that weight goes off into PC2, and PC3 and PC4 probably don't have that much weight anyway, because they don't. The standard deviations go down drastically.
Okay.
Now, as I said, you can either use the predict function or you just use the matrix multiplication on the original data to get the transformed data. So PC data. So PC1 is 0.503 times the sepal length, and this is sepal length. So sepal width, that's how you get PC1. You can plot. Okay, the plot function just drops off the standard deviations. It just it plots the variances. of 1, 2, 3, and 4. PC1's variance, PC2's variance, and so on. Notice the variance here between of these guys almost drops down to 0. If you keep the first two principal components, it's going to keep almost the entire variance in the data. See, look at the cumulative proportion. PC1 contains 73% of the total variance. PC1 and PC2 contain 95%. So you can drop off the other two, and you will still get 95% of the variance of the original information, original data. As I said, you can either use the predict function or you can use the matrix multiplication. You can observe this GG biplot. What it does is it observes what the original data are in terms of PC1 and PC2. So what it does is it plots basically between G is equal to GG biplot. So in terms of PC1 and PC2, what are the original, and it plots basically the data also. It just plots these are, and we have also plotted the different species in different colors. So it groups them by species. So we can see whether, the species colorings has some impact on whether PC1, within PC1 and PC2 itself, you can see whether you can nicely split off the species. So in the PC1, PC2 space, what is the petal width, sepal length, sepal width, and petal width? The original, in PC1, PC2 space, what are the original data? Basically, these are the four. The other two, sepal width, sepal length, and petal width are almost sitting on the same, direction in PC1, PC2 space. But sepal length and sepal width are separated out. Probably in PC3 and PC4, the petal length and petal width will be separated out. But in PC1 and PC2, they are almost sitting together in PC1, PC2 space.
Here the sepal width, the sepal length, and the petal length, they are all mutually perpendicular, right?
Yeah.
They are viewed in a three-dimensional space.
Yeah, so this is essentially PC1 is along the x-axis. Now we are looking at the original data in relation to the transformed coordinates. Essentially, it's like looking at you rotate. Suppose you rotate this image so that this becomes the x-axis, that becomes the y-axis, and then we look at the original x1 and x2 in terms of PC1 and PC2. That's what we are looking at here. Except that here, of course, there is a PC3 and PC4, which we have just ignored because you can't plot them. So we are just within the PC1, PC2 space. We are seeing what is the sepal width, what is the sepal length. See, and of course, see the petal width and petal length are sitting on top of each other. Which means to say that PC1 and PC2 are not the ones which are differentiating these two. They are being differentiated in PC3 and PC4 space.
Okay.
Whereas sepal width and sepal length are nicely separated out in PC1, PC2 space itself.
Okay.
And of course, the actual we have put different colors for the species. So we have given some color for species 1, species 2, species 3. What versicolor, setosa, virginica, and the idea is that in the PC1, PC2 space itself, you can neatly separate out the species. At least you can separate out this one. These two seem to be rather bit more mixed up in each other.
Sorry, your voice is breaking and it's going in a sinusoidal wave pattern. Sorry.
Okay. Yeah, but can you hear me? I mean, is it? Am I getting across?
No, we are able.
Okay, let me keep my mic closer to the. Just hold the microphone. So this is with the PCA. I think we'll stop there. The same thing can try out in some other cases as well. But the same thing they're doing. We haven't covered any of the other techniques, dimensionality reduction in SVD and factor analysis. Those two are also working on the same kind of data as PCA. So we'll be doing, say, SVD, dimensionality reduction, and factor analysis. Both of those also are about reducing the number of dimensions for a set of numeric variables. So it's the same thing. You can try out the same, and we just, I tried them out on the house pricing data just to see what impact it has on the accuracy. There is also, hello?
One doubt. Whatever we have been discussing is circle of correlation. Is that circle of correlation?
What is the?
Is this
one?
Yeah.
The circle here you're talking about. This circle. It's basically okay. It's okay. See, the circle is just to tell you what will be the length of each of these: sepal width and sepal length, and petal width, petal length, and so on. They are. This is the circle along which they can sit. Now remember this is a rotation. This is not a scaling. So the rotation has to make sure that it has to be sepal width, sepal length, petal width, petal length. They have to be along this circle. Know how else to explain that. This is a rotation between and PC1 and PC2 contain most of the information. That is 95% of the variance. You can drop off the other two almost. They are almost irrelevant. But this is a circle. I'm not sure why it's given. It's basically of size 2. Right, the circle is of size 2 essentially. It's not exactly. I thought it should be of just a unit size or unit radius, but all of the original variables, they have to be sitting somewhere in this circle. They have to be, because unless suppose it was less than this, that means that hello.
On the circle or within the circle?
Well, it has to be within the circle technically, because some of the component, some of the weight in that component can be in PC3 and PC4. But because PC3 and PC4 contribute to less than 5% of the variance, they are almost on the circle.
PC3, PC4 weightage less than 5%. PC1 and PC2 main weightage.
So we'll look at, say,
closer to the circle. Otherwise, it will be placed out inside the circle.
Overline over that. PC1, PC2.
PC1, PC2 PC1 x-axis.
See, what is the equation of the circle is just to tell you that, well, if it was all in PC1 and PC2, then so think of say the original data, say sepal length, or okay, let us look at sepal width. Sepal width is equal to some say call this as A1 times PC1 plus A2 times PC2 plus A3 times PC3 plus A4 times PC4. We know that, and I showed you that root of A1 square plus A2 square plus AC3 square plus A4 square is equal to 1, right?
Okay.
So in that, so basically that is an equation for a 4-dimensional sphere, something like the 4-dimensional equivalent of a circle. But if PC3 and PC4 contribute almost nothing, then you can be sure that root of A1 square plus A2 square has to be equal to 1, right?
Okay.
If A3 and A4 are 0, and let's look at the rotation matrix there. Log dot IR dot PCA rotation matrix here, and sepal width. Okay, sepal width here. This is A1, this is A2, this is A3, this is A4. okay, PC3 has some weight, but then the weight of the PC3, it has some weight on PC3 also. Sure. Okay, so it should not. It should. But then, okay, the weight on PC3 doesn't matter that much because of the variance. Not sure. Should be root of a1 square plus a2 square plus a3 square plus a4 square should be equal to 1. Sum of call sums or row sums. Row sums of IR dot PCA dollar rotation to the power of 2 is 1 1 1 1. So a certain weight has to be sitting on PC2, a certain weight is sitting on PC1, certain weight on PC3, and so on. And that is what is showing here. Supple width is equal to what? There is some, it is multiplied by some factor. I am not sure why. It should be, say, supple width. The variance along PC2 is
PC1 to PC2 original variables relationship PC1 PC2 அப்படிங்கிறது வந்து நம்ம டிரைவ் பண்ண ஆக்சஸ் இல்லையா, அதுக்கும் ஒரிஜினல் செப்பல் லென்த் செப்பல் வெயிட் பெடல் அந்த பாயிண்ட்ஸ் இத பிளாட் பண்ணிருக்காங்க. அவ்வளவுதான். இன்டர்பிரட் பண்றதா நீங்க பாத்தீங்கன்னா இந்த
so okay, this is some measure of how much weight is there along PC1 and PC2. If you don't have any, if you have lesser weight on PC1 and PC2, you should definitely have it on PC3 and PC4. This is okay. Here I think supple width is almost having the total weight on PC1 and PC2. Okay, it does have this much on PC3 and PC4 as well. But the most weight is on PC2.
Yeah, but their individual variances are very small, right? In the previous
their input to the variance itself is less. The total input of PC3 itself is less. Of course, it has to have some component on PC3 and PC4, but they themselves have lesser variance.
Right.
So we keep PC1 and PC2, and that explains most of the variance in the data.
Circular correlation.
So the interpretation, but the reverse தான். The US arrest பண்ணும்போது
இந்த மாதிரி ஒரு circular correlation
okay. Sir, from this graph we are interpreting that for example, the orange points are grouped together, the green ones are grouped together, or the blue ones.
Okay. The coloring of the points has been given in relation to their species. Let's go back here. They are using the species data, which we have not used in PCA. Remember, we have just dropped off the PCA. They are grouped it by species. So this drop. I mean, this got the coloring of the points has nothing to do with the principal component analysis. They have simply grouped them by species, just to show that within PC1 and PC2 itself, you are getting information that can be used to separate out the species. That's all it means. But it has nothing to do with principal component analysis. We have done PCA without taking into account the species data at all. We have dropped off that and then done PCA on the four numeric columns only.
Okay.
Okay, so I think so the coloring, just ignore the coloring. The coloring is just a matter of just putting one color for different species, which we have not used in PCA. What they have done is they have simply then split it by species to show that within PC1 and PC2 itself, you will be able to neatly divide out the species, right? You can easily use PC1 and PC2 itself to separate out at least this red color one. That is the purpose of showing that.
So what
Okay,
is
so
is that circle not about that circle of correlation? So that was the query she was trying to ask.
circle.
So
Okay, what do you mean by circle of correlation?
last week actually Professor mentioned about that circle of correlation. So the
We had
relation.
something similar graph like this, and we were trying to interpret like along the principal component axis how the along PC1 and PC2 how the actual values are located with respect to the new axis.
Yeah,
That we were analyzing. It was something similar. So I'm just trying to understand how to interpret this graph. Like, what do I interpret the relationship between the original values and the new axis? Now, what is the conclusion from the graph I get? That's what I'm trying to understand.
Oh, what?
Hello?
Yeah. So, okay, let's see. What are the values here? They may have multiplied by some value, some numeric value, but I don't see. Say, look at this. Petal length and petal width are almost sitting on top of each other. Now, look at petal length. PC1 is 0.7. I mean, the component along PC1 is 0.7. The component along PC2 is 0.03, which is almost 0. So that's the thing. See, but instead of 0.7, I'm seeing a 2 here. It's almost is almost coming up to 2. What is that? That's what I don't understand, because some kind of multiplication of that by what is sepal length? Sepal length is 0.5. So 0.5 has been converted to something like 1.75 for some reason. And okay. Let's see what's. This is actually a breakup of not just breakup of the components, but also weighted by some. Okay, I'll look at it and get back to you.
Sure, sir.
This is a breakup. Yeah, this is a breakup of components, but also it's not just the value. There's also some weighting by the variance as well. So some of this. So this multiplied by PC1 and the variance of that. That's what I think is plotted here. We'll just check.
Yeah, it's 0.57 and 1.7, getting 0.97.
Yeah, 0.56 multiplied by 1.7.
Yeah, it's around 0.9.
This is standard deviation. Here we finally will be interested in variance, not standard deviation. I'm not sure. I'll look at it and get back to you.
Sure. And one more question. The previous data set, whatever we were discussing, actual data set was having 80 variables. Like only 80 variables were there.
Yeah.
But
some of them were categorical, so I just converted them to dummies, and that's how we ended up with these 269.
Yes, but then we tried working with 100 variables, and we said we have reduced the dimensions. But even the original data had even lesser dimensions only, right?
Yeah. But notice that you how will be. How are you going to anyway do a linear regression? You have to you are going to do a linear regression by only converting them to dummy variables.
Hello, sir.
So can you hear me?
Sorry, we lost you. There was some confusion. So we lost you.
Okay. So yeah, you are saying that originally there were 80 variables, and then you bring it down to inflate them to 269, and then bring it down to 100. So you're not bringing down. But notice that the inflation to that many number of variables is necessary for linear regression, right? You have to convert them to dummy variables or do something to do a linear regression. So I'm comparing like with like. After there are other ways to handle the conversion to dummies. There are you can think of other ways to convert a categorical to numeric, but I just converted them all to numeric in order to do linear regression. That was necessary to do linear regression. But whatever you do, you take the categorical variables, convert them to numeric, and then you do PCA. And for linear regression, anyway, you need to have only numeric variables. So whatever means you use to convert categorical to numeric, you do that first, and then you compare PCA versus non-PCA. That's all I did.
Okay.
So you might say, okay, what is the use of PCA in that we had to first get them out and convert them to numeric and then only do PCA. Well, yeah, I mean PCA is a dimensionality reduction technique that works only on numeric data, not on categorical data. So you have to convert them to numeric. But notice that if I just use the LM model on the original data itself, the only way it is going to do LM is by using dummy variables. That is the only way it can do LM. So if you are sticking within linear regression, then PCA has definitely brought down the number of dimensions, right?
With the linear regression, we have used 269 variables. Now, because we have used PCA, we were able to find the most important dimensions, which were only 100 out of 269. And then we used the 269 variables to build the linear model. Is that right?
So I just compared the linear model that you build on all the data versus the linear model that you build on just the first 100 principal components. Now the linear model that you build on all the data can only be done if you convert the categorical to numeric, right?
Yes.
You can't build a linear model. So anyway, you have to do some kind of transformation to numeric. So that, and the simplest thing is dummy variables.
Okay.
So you can't build a linear model until you do that. So it's necessary. And then you bring down the number of variables and see whether you are actually improving the accuracy or not.
So PCA we have to do only if the data set has more categorical or factor variables. Otherwise,
no. PCA. Okay, so PCA is done whenever you have predictors which are too many. Whether they and PCA works only on numeric values. Remember. So if you have categorical data, you have to first convert them to numeric and then only do PCA. PCA is only working on numeric data, not on factors and characters. So I had to convert them to numeric for doing a linear model and also for PCA. So it was necessary.
Okay.
But you can't say that in so doing I have unnecessarily increased the number of variables. That you can't avoid. That increasing the number of variables is you can't avoid, because obviously it doesn't make sense to say that one column is just one column, whether it is a numeric column or it's a categorical column. Obviously a categorical column with 10 different possibilities is going to contain a lot more information than one column which is just a numeric column. Can you kind of feel it why that is the case? You can have a lot more possibilities, right?
Yeah.
And there's a lot more information in the sense that it is a multi-dimensional. You can't just put it as, you can't just see that if a column is numeric, then each value can simply be plotted as a point in a line. So the numeric value can just be pointed, it can be just represented by a point in a line segment. But but if it's a categorical data, it is a point in multi-dimensional space. You have, and if there are 10 different categories, it contains more information And what the dummy variables does is it shows that by splitting them up into various columns, multiple columns. So that you can't avoid.
For each of the unique values of the categorical variable, we are attaching a number and we are giving a column for that, right?
Yeah. We are just giving one column for each of the possibilities in the categorical variable, and under that column you put a 0 or 1. If it is that category, then you put 1, otherwise put 0. That is the way you convert dummy variables.
Okay.
Now, when we find the first few important dimensions, like one categorical column can have 10 different values. Like when we try to filter the top 100, only out of there may be cases like out of 10 categorical variables, only few will be included in that 100 and the rest cannot be included. Will that be a scenario?
Well, some linear combination will be included. You can't say which ones will be. I mean, that you have to look at which one is giving what weight to where. But yeah, you have to say some linear combinations will be important. Some linear combinations won't be important.
So the frequently occurring categorical variable will have more weight in the transformed column, right?
When I say what frequency occurring,
For example, say 100 rows, and if there is a column which can take 10 different values, it is not like 10, each of those 10 are going to occur some 10 different times. It may not be. One column will have this. 20 rows will have one particular value. The other probably about 30. The rest like that.
So let us look at an example. So one which will occur, so the thing is which will contain more information and which is going to contribute more to PC1. Let's see. Let's look at the original data. Train test. Yeah, can you hear me?
Yes.
Sir.
Okay. So you're saying that, well, suppose I say along alley, there is all NAs. There are a bunch of NAs. In fact, almost everything is NA, right? So now when you convert this to dummy variables, what does that mean? Well, what it means is that under alley, you will have, let's look at that. Oh, okay, alley NA has been dropped. So he will only have gravel and pave. Basically, that underscore NA has been dropped as the first, the first dummy, because I said remove first dummy. But the thing is, you have a bunch of zeros here, which means alley underscore NA should have a bunch of ones, right? Let's look at something else, say, where there are a lot of ones. So the thing is this, which of these columns, the dummy variables, is going to contribute more to the PC1? Can you answer that? Which one will contribute more to PC1? Is it the one with a lot of zeros or a lot of ones?
Lot of ones.
Actually, it is neither. It is neither the zeros nor the ones that matter. What matters to PC1 is variance. It is the ones which have actually 50-50 of each, which contain most information. And that is where the variance will be highest. So if it has a lot of zeros and very few ones, that means it is also conveying less information, right? The variance is less. Isn't that, can you see that? If you have just a bunch of zeros and no ones, in fact, if you have all zeros, then what is the variance? 0. If you have all ones, what is the variance? 0. So what matters is that if you have half zeros and half ones, that is the variable which is actually conveying the most information, because it's the thing that you can't predict in advance. If you see this column, I can predict in advance. It's almost all zero. So even if I don't know what it is, I can easily guess that it's 0, and I will be right almost all the time, right? So that column is not giving you much information because the variance along that column.
Okay, so the column being fixed will get dropped off, right?
Yeah.
The column, since it is being fixed, not because it is 0. Had it been 1111 also, it would have got dropped out. That's what you're
Had
saying.
it been 111 also, it will not contribute to the significant principal components.
Right. So okay. So then also it would have got dropped out.
Yeah, it would not have contributed much to PC1. That's what I mean.
Okay.
PC1 is going to look for that linear combination of the variables that has the most variance. This guy has so little variance that it's not going to contribute. It's not contributing to the important principal components. So whether it's all zeros or all ones, it means that the variance is 0. There is not much information that is being conveyed. Only if it is 50-50, then the maximum information is being conveyed. Because that variable conveys information, which you could not have guessed. So is that fine?
Yes.
Thank you.
Okay, we'll stop with that because we have not covered anything else. When is your next theory class with sir?
Tomorrow.
Tomorrow what time?
5:30.
Oh, okay. In that case, I'm supposed to join you also, but sir is teaching you theory as well. Fine, I'll also join. Ma'am asked me to join as well.
Oh. But I may not be there, sir.
Okay.
I sent the message. I may not be there. I'm just trying. So most probably I may not be there.
Okay, cool.
I just sent a message in WhatsApp that probably if there is a recording, I will try to catch up with you.
Can you send that code?
Yeah, I'll send it. IOA PA1, right?
Yeah.
Also, what's a PA1 combined? Do you have any?
Yeah, PA1 combined. PA combined, I guess.
PA combined.
IOA PA1 combined. That's where I sent.
Okay.
Oh.
Sir, one last question.
Yeah.
Hello. Like
Yeah, tell
I
me.
just want to understand why principal component analysis is part of unsupervised algorithm. Like we are here also we are.
Oh, okay. Yeah, well, PCA is not in itself. Now, I just used PCA and then built a linear model, but that has nothing to do with PCA. Remember, PCA is all about just bringing down the number of dimensions. I just used the linear model after PCA to show you what the impact it has in your actual model building, but that is another step altogether. That has nothing to do with PCA. PCA is simply about taking a set of that. PCA is just taking those 268 variables and bringing them down to 100 variables. That's all.
Then what is unsupervised algorithm here?
So it is unsupervised in the sense that it has no, there is no predictor, nothing like that in PCA.
But we are not predicting in PCA, right? We are just trying to reduce the dimensions. We don't do any prediction.
Yeah, that's right. We are not predicting anything. There is no outcome. Now, of course, we use the predict function, but as I said, that is just that is kind of confusing. So ignore that. It is simply an attempt to take a bunch of variables and bring down the number of variables, take a linear combination of them, and get out new variables that are fewer in number and still contain as much information as the original variables. So it is unsupervised because there is no column which you consider as the predictor and the predicted. There is no outcome that you're trying to predict. In a sense, there is no one predicted or column and all the others are predictors. It's not like that.
That's why we call it unsupervised algorithm.
Yeah, that's why we call it unsupervised. That is, there is no label. You cannot, for example, ask what is the accuracy of a PCA. It doesn't make sense because there is no outcome that you're predicting. You can't compare it with some actual outcome and see, right? Doesn't make sense. Now, of course, you can say that I keep the first 100 variables, I keep this much, but that is our choice. How many you drop off. But PCA in itself is not some kind of a predictor that can then be compared against test data to check whether it's accurate or not. It's not that kind of thing. So it's only working on a set of numeric data which are all on equal footing. So all those 268 variables that we work with, they are all on equal footing. There is no predictor, predicted. You're using the entire set and taking a linear combination and pulling out a subset.
Okay. Okay, sir. Thank you.
Okay, so that's it. We'll just see whether thing works. IOA PA1 combined. IOA hyphen PA1 oh yeah, I have it. So how are you all doing? How's Chennai? Chennaiல மழை பெய்யுதா?
Only parts of Tambaram. That side.
Yeah, you need Chennai.
துர்கா போயிட்டு வந்திருக்காங்க, சவுத் சைட் போயிட்டு வந்திருக்காங்க. பட் அவங்களும் அங்கேயும் வந்து ஒண்ணுமே இல்லையா, பங்குனி வெயில் பல்ல காட்டுதுன்றாங்க. அங்க எப்படி சார் இருக்கு உங்களுக்கு? பாம்பே எப்படி இருக்கா? What do you find it?
Bombay, yeah. So it's been great. I've a lot of good people are there to help me. I found accommodation.
Oh, excellent.
Are settling in. I found a room, a 1 BHK apartment. My wife will come later. Now I'm just alone. I will come another 2-3 months or so.
Self-cooking.
That no, I haven't learned cooking and all. I'll just buy out and eat. That's all.
Okay. But how do you find the office environment?
Oh, office. Yeah, there are about 200 people totally, and 30 people are into analytics. But it's a very rudimentary, kind of work they are doing. They have just been using logistic regression for almost everything. Linear logistic regression. That's all they have been using so far. And now only they are thinking of expanding and looking into all the other techniques, whether they'll be useful. And they are also very interested in exploring beyond credit scores. I initially thought that it was only credit scores, but they want to try out some other fields altogether. Even health analytics. They are interested.
That's it. Yeah. Interesting. So you have a lot more to learn than that case, right? It's not just modeling then. Okay.
Yeah, so they want to expand out. In fact, right now, so all those people are now getting courses. They're teaching courses in Python and all here. The rest of the group. I don't need it, of course. I'll see whether I myself will be teaching them something if necessary. If they are going to be using machine learning, I'll be teaching them.
Right. So you will have application of machine learning there. Okay, it's not just predictive or it is not just model building, and it is involving machine learning also there.
Okay, depends on what you mean by that. I mean, so far they have been using only linear logistic regression. Now they want to go into some of the more advanced techniques.
Oh, okay.
Yes. So far, in fact, the whole job of Experian credit scores has been just identifying, say, who are the people likely to commit fraud, who are the people likely to default on loan payments, etc., and then give some kind of risk analysis. And the whole thing has just been logistic regression to predict a binary classification. Okay, and everybody has been working on only that. That has been the entire staple. But now they want to expand out and try out, say, some kind of image analysis and a lot of other things. And they brought me in for that. They want to do some, and for that, of course, you need to use ML algorithms. ML. They have a lot of people. They have people from IIT and all, but they don't have people trained in ML yet.
Oh, that's interesting. You will definitely have a better edge over them in that case. That will be interesting.
Oh yeah, my job is to train them. My job is to train them in ML.
That's very nice.
Main thing.
Very nice to hear this. Very nice. Very nice. Yeah, keep us with more information like this so that we will also learn. So, thanks for the session.
Yeah, sure.
Take care.
Sure.
Thank you. Thank you.
Yeah, take care. See you.
Thank you. See you. Bye.
மண்டே மண்டேவா
நாளைக்கு லீவு. நாளைக்கு
கிளாஸ் இல்லையா?
நாளைக்கு ஈவினிங் கிளாஸ் மட்டும் ஷூரா தெரியல.
ஏன்னா நாளைக்கு கிளாஸ் இருந்துச்சுன்னா நான் மறுபடியும் பார்க்கலான்னு தான், அதுதான் கேட்டேன்.
இல்ல நாளைக்கு ஈவினிங் கிளாஸ் கன்ஃபார்ம் பண்ணி சொல்லுவோம்.
கன்ஃபார்ம் பண்ணி சொல்றீங்களா? அப்படின்னா மண்டே கூட அனுப்புவோம், ஒன்றும் பிரச்சனை இல்லை. ஆனா நாளைக்கு கிளாஸ் இருந்துச்சுன்னா தேவைப்படும் மறுபடியும் ரிவைஸ் பண்றதுக்கு தான்.
சரி, ஓகே.
ஓ சார் அவைலபிள் இல்லையா?
சார் வந்து உடம்பு சரியில்லை அவருக்கு.
ஓகே ஓகே.
அதான் நாளைக்கு ஷூரா தெரியல.
சரி ஓகே. அப்படி இருந்துச்சுன்னா சரி நாளைக்கு லஞ்ச் முன்னாடி கூட அனுப்புவோம். ஓகே. இன்னைக்கு நைட்டு கூட வருமா?
நைட்டு நாளைக்கு காலைல கூட வரும்.
சரி ரைட்டு.
பாய்.
சரி ரைட். பாய்.